and what STP does for us in our switched environment. The first thing we'll take a look at is some of the issues that we'll face in our switched environment and how do we solve it. We'll take a look at having a single point of failure between different switches. Let's say I have two switches over here, switch 1 connecting to switch 2, and I have PCs on both the switches. If I connect the two switches to each other just using a single link, and that link fails, what happens is all the communication between the two switches fails. So to solve this issue, one of the things that you can do is put two cables to connect switch 1 and switch 2 to each other. Okay? So this will solve our single point of failure problem by introducing redundancy into the network. But when you insert redundancy into the switch environment, there's certain issues that pop in. All right, we'll take a look at those issues that are there because of the redundancy, which solved another issue, which was a single point of failure. Now the next thing is, how do you solve the redundancy issues? We'll take a look at those issues first, and then we'll analyze what STP brings to the table to solve those issues. Once we're done with that, then we'll take a look at the evolution of STP, the different type of STPs and how they progress from one to the other. All right, and that's the objective of this particular video. So let's get started. The first thing is, when you introduce redundancy into your network, why do you do that? When you have a connection between two switches and it's a single connection between the two switches, if that link goes down, any communication that is taking place between the multiple devices on one switch is broken to all the different devices on the other switch. The trunk is broken. All right. So if you have a single connection between the two switches and it breaks down, you have this issue of a single point of failure. All right. So to overcome that, we add another link, as I said in my intro, and this is what the network will look like now. I'm just showing you one PC over here. Think about having multiple PC 1, 2, let's say 3, and these might be clients or these might be servers. 4, let's say I have 5, I might have 6. Now what's happening is, if this link had gone down, I would just lose the communication to PC 2. If this link goes down, I would just lose the communication to PC 5. But if this link had gone down, I would have lost all the communication between all the devices on one side to the other. So it becomes imperative that you provide some type of redundancy between the two switches. All right, this is a common thing to do. And later, in the later videos, we'll also talk about how we can optimize this dual connection between the two switches by using what are known as port channels. But for right now, let's keep port channels out of the discussion right now. We'll take a look at that later on. So we have introduced these dual ports between the two switches. Is there an issue that comes in? Absolutely. And that's what I want to introduce to you guys over here. What are the issues that come in if you have dual links between switch 1 and switch 2, and how does STP solve that issue? Let's take a look at the two connections between switch 1 and switch 2 right now. Now, what happens is this. Let's say this PC over here sends a broadcast. He sends an ARP broadcast, which is, or ARP request, which is a broadcast. Any broadcast that comes in has a destination address of at layer 2, because the switch is forward at layer 2, of all Fs. Broadcast means flood it. Flooding of the broadcast takes place on all the ports except for the port it came in from. So if PC1 is sending a broadcast into switch 1 over E02, it's going to come in over here. It's not going to send it back towards PC1, but it definitely is going to send that, and I'm going to use different colors over here so that we don't get confused. It's going to send it over E00 to switch 2, and it's going to use the second link, if it was there, to send the broadcast to switch 2. First problem has already occurred. I have received 2 frames on switch 2 that are identical. It's the same broadcast that has gone to switch 2 over 2 active links. Now when switch 2 receives it, it is going to forward the broadcast to all the ports on that particular switch. So that means that I am going to get how many broadcasts sent to to PC2, the same broadcast. So now I have a duplication of packets. That's the first issue. The other issue is when the broadcast was received. I'm going to focus on one of the broadcasts for right now. Let's start with the green. When the broadcast was received on switch 2, it would not send it back on E00. It would send it to this guy, but it would also send it to all the other ports, including E01. So this green broadcast goes down over here, back to switch 1. And the red broadcast that came in from E01 will not go back on E01. It would have sent it over here, but it would also send that red broadcast back over here. So the same broadcast that came in onto switch 2 is sent back to switch 1, the originator. Now I'm going to turn the green into another color so we can keep on doing this. The green came in of E01. It is not going to go over here. The broadcast now comes back to PC1. Not only that, it will also turn around and go back to switch 2 on the other interface. The red one that came in, I'm going to put a different color for that, let's say brown. The red one that came in, again, is going to do the same round over here. And guess what? It's an endless process. This is known as a broadcast storm. A layer 2 broadcast storm, and eventually it is going to create so many flows that the entire switching environment will come to its knees. And the reason it happened was because of the redundancy, because I had 2 active links between the 2 switches. It caused both the links to forward that broadcast to the other side. So how do I avoid that? So it's not a good thing to have redundancy in this case, because the same packet would come back to me. And that's where STP comes in. The first role of STP is to break a loop between switch 1 and switch 2. If you have redundant links between 2 switches, it is going to break the loop between the 2 switches by disabling one of the ports on the switch, between the 2 switches. So as soon as it detects that switch 1 and switch 2 are connected to each other over 2 links, what it automatically does, it puts one of the ports in the blocking state. So that's the first thing it does. So it only allows forwarding to be done on one port. Even if I had 3 redundant ports, it's only going to allow forwarding between switch 1 and switch 2 to be done based on one single active port between the 2 switches. All right. So in this case, when the frame came in into switch 1, switch 1, this is blocked. I would only send it over here. That frame cannot come back, because once I receive a frame on a particular port, I won't send it back on that one. It would send it over here. So single port, which is the right thing to do. All right. How does it determine which port to use? They're all equal ports, but the way it determines it is it uses what is known as a port priority. Which is a value, it's a numeric value. It goes in blocks of 16. The default is 128, but all the ports are set to the same number. So unless you go in and you want to select a particular port, it will use the lowest port to do the forwarding. So lowest port priority to do the forwarding. So 128 is the default. So all of them are set to 128. So what's a tiebreaker? The tiebreaker is your port MAC address. Every port has a MAC address assigned. The MAC address is generally on the switch. You have a system MAC address, which is for the switch itself. And then there's a MAC address assigned to each and every port. Now, on the ports, the MAC address is in ascending order. So this one would have the smallest MAC address, or the smallest number in terms of the MAC address. This is going to be the largest number in terms of the MAC address. It's incrementing. It's in the ascending order. So generally, this would be the smallest MAC address, or the lowest MAC address. All right. So if the port priority of the 2 ports is the same, it uses the lowest MAC address, which is generally going to be the lower port number. So if this is the case, my guess is if I haven't changed my port priority, this port will be forwarding and this port would have been put into the blocking state. All right. So again, port priority takes precedence. If the port priorities are not changed, it is the MAC address of the interface, the lower MAC address, that gets selected as the forwarding port. So that has taken care of, STP has taken care of a loop between what? Two switches by blocking one of the ports. Good so far? So that aspect has been taken care of, but there is another aspect that we haven't taken care of yet, and that is our overall loop. So right now, based on my lecture so far, we have blocked one of those ports out of each one of those dual links between the three switches. So right now, the way it looks is this. My forwarding ports are these. Good so far. So single link between switch 1, switch 2, switch 3. STP does not just stop between two switches. It also analyzes loops that are in the overall network. Now I have switch 1, switch 2, and switch 3. If you take a look at it, let's take a look at the same broadcast that took place, or broadcast storm that took place in the previous example. So PC1 sends a broadcast out over here. It's not going to go over two ports to switch 2 or switch 3, but it does go over the active port over here. I only have one active port with switch 1, so it's not going to go back over there. But I do have an active port towards switch 3. I'm going to forward it to switch 3 like that. I'm going to forward it over here. Good so far? Now this, at the same time, PC1, the same broadcast would have gone over the active port to switch 3. So right there you have an issue. Although STP had blocked, initial thing that I talked about in terms of STP had blocked the loops between the two switches, overall the loop is still there because the same frame that came into PC1 was forwarded to E00 and E02 towards switch 3. So right now I'm going to receive what? Two frames already on PC3, but that's not it. Once I receive it, the green frame that came in from E02, although it's not going to go back on E02, it is going to go back to switch 1 over the other port. The red frame that came in from here onto switch 3 will make it back to switch 2 over E3, not E3, E2, the forwarding port, the blue forwarding port over there. All right, and switch 2 will forward that over the forwarding port over here to him. Does that make sense? Again, the loop takes place. The port, the frame that came in from E02 is going to make it back over here. This red port, the red frame that came in over here is going to make it back over here, and the endless loop is there. So STP doesn't just solve the issue over here, it also looks at any loops in the entire switching environment. And the way it does it is by sending a special packet known as the Bridge Protocol Data Unit, BPDU, between the switches initially to discover the entire topology of the switched environment. Once it discovers the entire topology, that's like a protocol, a routing protocol that uses at layer 2 to communicate and discover the layer 2 topology. Once it discovers it, it also discovers all the different loops are there that exist in your network, and it automatically blocks the loop in this environment as well. It would block, as we had discussed, we only have what, one port each going on, because the other ports were blocked because of the loop that was created between the two switches. Now I have one port each running. Among them, it will also block one of the links to block the loop between switch 1, switch 2, switch 3. At the same time, let's say hypothetically speaking, I also had another switching environment over here. Okay. It would also find out that there is a loop going on between switch 4 and switch 5 and block one of those ports over there as well. Let's say I'll block this one. So any loops that you have in the switching environment, STP will go ahead and block that port. That's the job of STP. All right. So with that in mind, let's go ahead and take a look at the slides and see what the slides have to say about it. This is the issue that I talked about in terms of the the multiple frames that are being sent. PC1 will send a broadcast from frame 1 to broadcast frame to switch 1. Switch 1 will forward the broadcast all ports except the port it came in from. The whole thing that I went through is basically listed over here. This will continue on to switch 1 and the frame will be transmitted back to switch 2. This is the endless loop. This is known as the broadcast drone. This is what I explained to you graphically. I've also shown it to you within your slide as well, or documented that for you guys. And then what does STP do? STP not only works between the two switches as I talked about, but also for the fully switched network like the one in the previous slide. The previous slide being this guy over here, where it basically will block not only the ports over here between the two switches, but it'll also take a look at the overall topology and block it over here. All right, just for the heck of it, just to make sure you get the point. So now I have this completely blocked, this completely blocked, this completely blocked, this link blocked. All right, this is completely blocked because that avoids a loop. But let's say I connect this fourth switch over here, like this. There's no loop over here, but now if you take a look at it from again a grander scale, there is a loop between switch 1, 2, 3, and 4, because this is going to cause a loop again. So again, the switch will go in and block one of those ports. Which port it blocks, we'll analyze that in a second. So these are the blocked ports now. So the forwarding ports are switch 1 to switch 2, switch 1 to switch 3, switch 2 to switch 4. All the other ports are blocked, so you can avoid loops. All right, this STP does on its own. So how does it do it? Let's take a look. So not only does it block it between the two ports between two switches, STP also blocks it in the entire network. How does it do it? How does it know which ports to block? In this particular environment, what STP does, first thing, it sets the center of your network. The center of your network is called the root. All right, so switch 1 becomes the root switch, let's say hypothetically, and I'll show you how you can elect one of the switches, because you know your topology better than the technology does, because you cabled it up, and one switch might be more important than the other. This is at the center of your switched environment, so you want this to be the root, the center of your network. So you, based on certain parameters, can specify that this is your root switch. Just like you had the port priority to pick the two ports between the two switches, there's also a switch priority that you can control, which allows you the ability to specify which is the root switch. So let's say, for argument's sake, this is my root switch. I've already blocked these ports over here. Now how does it know which port to block among the loop between switch 1, switch 2, switch 3? If this is the root, the link that is the furthest away from the root is the least preferred link in this particular loop. So in that case, if this is the root, this should be forwarding, this should be forwarding. To block the loop, I need to block this link. So this becomes my blocking link because this link is the furthest away from the root. Let's say hypothetically we selected this as my root, and it's up to you. You have the ability to control it. Let's say this is my root switch. Now this link is the furthest away from the root, so this is going to be blocked to block the loop between switch 1, switch 2, and switch 3. So this link will be forwarding one of them links. So E02 to E00, the link between switch 1 and switch 3. E03, E03, actually it would be E02 because remember the port priority thing that I talked about. So E02, E02 would be forwarding between switch 2 and switch 3. Why? This is the root switch. This is the segment furthest away from the root. That's the one that is going to get blocked. This is called the path cost. Path cost is basically the cost of that segment from the root switch. Good. So the first thing that you need to do is elect your root of your network, and that's the first thing that STP does, and it's done automatically. You can either call it root bridge, which is an older technology. Now they call it a root switch. Most of the new switches that you go to and you check the show spanner tree commands, the verification commands, they will refer to this as a root switch. How do How does STP select the root switch? As I said, it is done based on the switch priority. Every switch has a switch priority assigned. The switch priority, just like the port had a port priority, switch priority is a bigger number. It is 32768 by default. The range is 1 through 65,535. It's a 16-bit number. But if you don't change the switch priority of any of the switches, the tiebreaker again is that system MAC address. Remember earlier on in this video, I told you that every switch has a MAC address assigned not only to your ports, but also to the switch itself, called the system MAC address. The lowest system MAC address is the tiebreaker in case the the switch priorities are the same. All right. So you can either manipulate the root switch selection by changing the priority of the switch. If you don't, the system automatically will pick the root switch based on the lowest system MAC address. And that's something that you might not want to do, because generally what happens is when you have system MAC addresses, there's a good chance that the lowest system MAC address will be assigned to the oldest switch. And the oldest switch might be an access layer switch someplace that you may not want in the center of your network, might be towards the edge of your network. So you don't want STP to automatically pick your, pick your root switch. So it's recommended that you actually go to your center of your network and manually select your root switch, or you can also set up a backup root switch. We'll take a look at that in the next video in terms of how to select a root switch. Once the root switch is selected, now STP will figure out the the physical topology by using the BPDUs. If it sees a loop anywhere, it will block that port. And the segment that will be blocked is the port that is the furthest away from the root switch. All right. And how do I make sure there's no loops that take place? What STP does automatically is when a port comes up, let's say this is my first switch that's up. When a new port comes up, now both these ports will come up. Let's say both switch 2 and switch 3 are coming up. When they come up and these ports go live, as soon as they come up, what STP does, it does not let it forward any data frames. Forwarding is blocked. Instead, what they do is data forwarding. So there's no data frames that can go across initially. The first 15 seconds, it listens for BPDUs. It's just listening. Once it listens to the BPDUs, it creates the actual topology by learning. So the first 30 seconds is a timer that it takes to figure out the physical topology, and if there are any loops, what does it do in the first 30 seconds, 15 and 15, total of 30 seconds? It will discover the loop and block it. It would have blocked this one, it would have blocked this one. Both these ports are going to be blocked. So it makes sure that no loops are there, because as soon as a port comes up, even when the PC port comes up, it's not going to forward for the first 30 seconds. Why not? For the first 30 seconds, it goes into 15 seconds of listening, 15 seconds of learning. Once it learns the topology, it says, oh, there's no loops over here. It's an end device. I haven't received any BPDUs from it. Guess what? At that time, it goes into the state known as the forwarding state. So you need to understand, by default, when you go and configure a switch, the switch port will not forward immediately. It will wait for 15 and 15, 30 seconds total before it starts forwarding, because it needs to make sure that this new interface that has just come up is not causing any loops in the environment. Good so far? So that's something that it does, and that's what I've documented for you guys over here in this particular slide. When a port comes up, STP does not allow it to forward traffic immediately. It puts the port in the listening state. It will listen for the BPDUs, and it then transitions the port into learning state. In this state, the STP determines if any loops might be created by this port. If not, the STP transitions into the forwarding state. This time will be 30 seconds. Why 30 seconds? To break it down, 15 seconds for learning and 15 seconds for listening. All right? So that's the 30 seconds over here. So any port, by default, when it comes up, we'll have to wait for 30 seconds before it starts forwarding the frames, the data frames I'm talking about. At this time, the only frames that are going across are your BPDUs. The BPDUs are the system frames that are determining the topology for you. Now that we know what STP does, let's take a look at the different flavors of STP that existed or that we have gone through to get to the stage that we are at right now. The first form of STP was called the common instance of STP, or CSTP. All right, what is this? In this type of setup, this is pre-VLANs, because there was one network, you would have one root switch, the other ones for the entire topology, the other ones were non-roots. So this one would be blocked, this one would be blocked, this one would be blocked. So this link is completely blocked, one link each blocked on the other ports. Now, initially that was the case, but then Cisco introduced the concept of VLANs. Now you had multiple VLANs over here. So let's say I had 4 VLANs or 10 VLANs, let's say. I had VLANs 1 through 10. Now for all 10 VLANs, there was a single instance of STP. So this would be the root switch for the entire layer 2 topology, regardless of what VLAN. So this port would be blocked for all the VLANs. So if this PC wanted to communicate to this PC, the data flow, the frame flow would be this guy over here, here, and here. It would not take the direct path. And this direct path is completely lost to avoid loops. That is CSTP. So common instance of STP, assuming one spanning tree instance for the entire bridged or switched network, regardless of the number of VLANs. This implementation, you just have one spanning tree instance, so you need to maintain one root, one single BPDU send for all VLANs. Single root switch for all the VLANs. If a port is blocked, it is blocked for what? All VLANs. This is also known as the traditional spanning tree protocol, the old one with a single instance of STP. So what's the drawback? The good thing is it's STP, it blocks the loops, but the drawback of this type of setup is that I have this segment completely not utilized. This is there just as an insurance policy. Just in case one of the links over here goes down, now I can use this to unblock it, and that STP would do automatically and then start forwarding where? On this link. All right. Otherwise, there's no utilization of that link between switch 2 and switch 3 in my topology, just to get a point across. Now that's where they decided to come up with another type of STP, that is IEEE, which was called per VLAN STP. As the name suggests, every VLAN would have its own instance of STP. So in my case, where I had 10 VLANs, I would have 10 STP instances. That means I could potentially have 10 devices acting as the root switches. All right. I would have 10 BPDUs sent. For each VLAN, I would have a separate BPDU sent. The BPDU is a protocol that is not only used for learning the topologies, it is also used as a keep alive. You remember how the routing protocols EIGRP and OSP have used to have that keep alive to make sure the other route is still up? Same thing applies over here in PVST as well with the BPDU. Now, because of this, there's goods and bads. What's the good part about it? I have the potential. Let's just take 3 VLANs for right now. Let's say we'll take VLAN 2, 4, and 6 as an example. What I could do is for VLAN 2, I could say switch 1 is my root switch. How do I do it? I change the priority of the switch for VLAN 2. So when I have multiple instances of STP, I have the ability to pick the root switch, change the switch priority per VLAN. So I can basically say for VLAN 2, the switch priority for switch 1 is 0. That's the best. The lower the better. Okay, but at the same time, what I can also do is for VLAN 4, I can go to switch 2 and say, I want you to have a switch priority for VLAN 4 as 0. So in that case, this guy will become the root switch for VLAN 4. And similarly, I can do the same thing for what? This guy saying your switch priority for VLAN 4 is 0. So this becomes a root switch. Now by doing this, what happens is for the green, which is VLAN 2, this port is forwarding, this port is forwarding, this one will be blocked. Actually, I should put this is blocked. Okay? But at the same time for red, this is the root switch. So this port is forwarding. This port will be forwarding for what? At least this link is being utilized for VLAN 4. And this guy would be blocked. So the blocking now is taking place selectively per VLAN. So at least I'm getting some utilization of the link between switch 2 and switch 3 for the traffic that needs to go for VLAN 4. And then the third one is the orange one. This is the root switch. So I'll be forwarding on this link and this link. The blocking link would be this guy. You get my point, because there's different instances. Now at least I'm getting full utilization of my topology, not completely, but at least I am maintaining a redundant environment and at least utilizing some part of that link for some traffic. Now the different ports and different VLANs would utilize that. All right, that's the advantage of doing per VLAN STP by selecting different switches as root switches. And that's what this is all about. So analyze this. Each instance could be configured with a different root switch or bridge, whatever you want to call it. Since PVST treats each VLAN as a separate network, it has the ability to load share by forwarding some VLANs on one trunk and other VLANs on another trunk without causing an STP loop. And I showed you how that's done. The drawback over here, because I have multiple VLANs, I need extra overhead for what? Maintaining separate STP instances. So multiple BPDUs will be sent. So that's the drawback. It's the overhead that will be caused by doing this, PVST. But it's the price that you pay for utilizing all the links and keeping a loop-free environment and having redundancy. All right. Now, this is good. This is fine. Then what Cisco did, Cisco came up and said, okay, this is great. STP is fine. It's working properly. I have avoided my loops. All that is good. But the problem that I have is a lot of users are complaining when they plug their PC, their device, or their device comes up and connects to the network. For the first 30 seconds, I'm not doing anything. The 30 seconds are lost. The first 30 seconds are always lost in what? Listening and learning. Why? Because the switch wants to make sure when a device, a port comes up, there's no loops. Okay? So what Cisco said was, well, this is great, but you know what? I know as the administrator that this port is connected to a PC. It's an end device. It's not a switch. So it's not going to cause a loop. Why do I need to have my users wait for what? 30 seconds before the port comes up. Let's do something in which the administrator has the control of designating certain ports as what? Ports that are not going to cause a loop. My guarantee, the administrator says that. So on these ports that are connected to end devices, you have the ability to skip the listening and learning states and go into what state immediately? Forwarding states, if the administrator goes in and configures this port in such a way that it's connected to an edge port, edge meaning an end device. It's not connected to a switch. So if the administrator goes in and configures that port, Cisco said, let that port come up immediately because I trust the administrator's judgment to know what his network looks like. This is enhancement of PVST was done by Cisco. And anytime you see a plus against a protocol, understand that plus comes from the fact that there are certain vendor specific modifications. Anytime you see a plus against a protocol, that's the indication. And that's exactly what Cisco did. So Cisco enhanced the 802.1q specification, and it was called PVSTP plus. And what was that? Faster conversions by using technologies like PortFast. Okay? PortFast is now, or PVST plus is something that started running on all the Catalyst switches. Catalyst are the series of switches from Cisco. All right? So this allowed you the ability, the main ability of PVSTP plus over PVST. PVSTP plus has all the PVST features plus these enhancements, this PortFast capability. So that's what Cisco did to bring it up and enhance it. Well, when IEEE saw this enhancement, they said, this is great, but we want to do this as what? As an open standard. And they said, let's incorporate the same type of feature in the standard STP. And they did that. And that came to be known as rapid PVSTP. So it came from the PVSTP plus implementation, which provides for what? Faster conversions. So this one would include features like the Cisco PortFast feature. All right. And it has some enhancements. There's other background enhancements that are also done in terms of configuration. It keeps backup ports and all that. And it is compatible with the older protocols of CST. So even if you don't have PVSTP on all the different devices, it's backward compatible. This is called rapid PVSTP. Rapid PVSTP in one way is the standardized version of what? These two are somewhat similar. This is an enhanced version, a better version of the same thing. So initially, you had PVSTP. Cisco came out, enhanced it by enabling features like PortFast, enhancing the overall workings of it. They called it PVSTP plus. IEEE came out and said, this is a great feature. Let's incorporate it, make it a standard, and clean up tweak it a little bit. And that became rapid PVSTP. Nowadays, the most common used STP version is rapid PVSTP. All the newer switches from Cisco, they don't come up with PVSTP plus. They have the rapid PVST standard available. This actually, on most of the switches, is the default STP implementation on the newer switches. All right. So this is rapid PVST. There is another one that's beyond the scope of this class, which is called the multi-instance STP. We'll talk about that in the switching class, the CCNP switching class. But to recap, we took a look at the single point of failure and how redundancy solved that issue. But the other issue that came with redundancy was loops, and how STP solved that redundant interface issue causing loops. Then we took a look at the different STPs that you have. You have the common STP, which had a single instance for all the VLANs, one single root switch for the entire switching environment, which was enhanced by IEEE by using another better version of STP, or not a better version, a different version, where each STP, each VLAN would have its own STP instance. All right, that allowed me the ability to utilize all the links on my switched environment, not for the same VLAN, but for other VLANs. So link 1 might be blocked for one VLAN, but it's forwarding to the other for the other one. So load sharing capabilities. So this was something that everybody liked. Once this was in place, Cisco came in and said, let's enhance it for the edge ports, the end ports, by including a feature like PortFast. There's other features, like there's an uplink fast feature, There's a backbone fast feature. There's other features that allow you enhancements in terms of convergence time, which we'll take a look at in the CCNP switching class. So Cisco came out and proprietarized this by calling it PVSTP plus. IEEE came back and said, let's standardize it. They liked what Cisco had done. Rapid PVST came about, which was PVSTP plus with some additional internal enhancements, and that's what you have right now. As I said, there's another STP that's out there, which is multi-instance STP. We'll take a look at that in the CCNP switch class. Hope you guys enjoyed it. We'll do some labs now regarding STP in the following videos. Thanks for watching.